Okay, here's part 2 of your lesson, and everybody loves a good trig problem, right? So let's find the intervals on which f is concave up or down, the points of inflection, the critical points, and the local maxima and minima for f of x equals cosine squared of x on the interval from 0 to pi. All right, what if we write f of x as the cosine of x with the squared on the outside? Remember, that's what it means, but that will help us with our chain rule. So let's find the first derivative. That's going to be, using the chain rule, 2 times cosine x times the derivative of the inside, which would be negative sine x. Derivative of cosine x is negative sine x. So our first derivative is negative 2 cosine x sine x. We want to find where that equals 0 or does not exist, and it always exists, so let's find where that equals 0. Let's divide both sides by negative 2. And then let's set each factor equal to 0. So cosine x equals 0, sine x equals 0. You have to think about your quadrantal angles. Cosine at 0 radians is, or at 0 radians we have the 0.10. At pi over 2 radians we have the 0.01. At pi radians we have the -0.10. And at 3 pi over 2 radians we have the 0.0 -1. The x-coordinate is the cosine and the y-coordinate is the sine. So cosine of x equals 0 when x is pi over 2 and 3 pi over 2. Oh, but we're only going to pi. So we don't need 3 pi over 2. Okay. And then sine of x equals 0 when x is 0 and when x is pi. But those are the endpoints, so we're not going to count those as critical points. So the only critical point is x equals pi over 2. Okay, so we got one thing. Check that off. Let's find the... Hey, it doesn't ask us for the intervals of increasing and decreasing, so we could just move on to the second derivative now. To get the second derivative, let's take a look at this version of our first derivative right here. And let's leave the constant out front, leave the -2. I'm going to need some more space, so I'm going to erase my unit circle. Leave the constant -2, and then we need to use the product rule. So we have the first, cosine x, times the derivative of the second, derivative of sine would be cosine, plus the second, sine x, times the derivative of the first, derivative of cosine would be negative sine. So this is going to be -2 times the quantity cosine squared x minus sine squared x. Wouldn't it be awesome if it was cosine squared x plus sine squared x, because that would just be 1, but it isn't. Oh well. I think we do have an identity for this. Cosine squared x minus sine squared x is cosine of 2x. Does that sound right? It's a double angle identity for cosine, I do believe, which maybe that would come in handy in the next few steps. We shall see. Okay, what we want to do with this is find the potential inflection points. So let's go ahead and set this equal to 0 and divide both sides by -2. So cosine squared x minus sine squared x equals 0. I'm going to add sine squared x to both sides. And I'm going to divide both sides by cosine squared x. And that gives me 1 equals sine squared x over cosine squared x. And do you know why I did that? What is sine x over cosine x equal to? Yep, it's equal to tangent x. So this is 1 equals tangent squared x. And then if I square root both sides, I get plus or minus 1 equals tangent x. So what angles have a tangent value of 1 or -1? Do you remember? Let's see. We could draw a little sketch. Make a reference triangle. If the tangent is 1, then opposite over adjacent would be 1 and 1, and that would be a 45-degree angle. and that would be pi over 4 radians. And we would have another one in quadrant 2 because we have a negative one. We would have another one in quadrant 3, another positive one, and another negative one in quadrant 4. However, remember the interval only goes from 0 to pi, so we only want quadrant 1 and quadrant 2. So x is pi over 4 and 3 pi over 4. Those are the potential inflection points. Okay, what do we want to do now? What's left on our list? Find the intervals on which f is concave up or down, the points of inflection, the critical points, and the local maxima and minima. Okay, so let's run with what we have so far here with the second derivative, and let's split the number line into intervals at those potential inflection points. So we have 0 to pi over 4, we have pi over 4 to 3 pi over 4, and we have 3 pi over 4 to pi. And what we want to do is pick a number in each interval and test it into the second derivative and see if we get a positive or a negative. So I think I'm going to put this function into my calculator. What function am I putting in? The second derivative function. So I'm putting this thing here with a -2 and everything into my calculator. Okay, and now I'm going to use my table, and I made sure that my calculator was in radians. And for a point to plug in between 0 and pi over 4, I just typed in 0.1, and I got a negative. So the second derivative is negative. For a point to plug in between pi over 4 and 3 pi over 4, I'm going to be strategic here. I'm going to choose my critical point, pi over 2, and you'll see why in a minute. So we plug in pi over 2, and we get, for the second derivative, we get a positive. And then for something between 3 pi over 4 and pi, I'm going to pick 3.1, because we know 3.14 is about pi, so something smaller would be 3.1, and that gives me a negative. So what does that tell me? That tells me that f of x is concave down, then concave up, then concave down. So where are we? Now we have intervals of concavity. So we can check that off the list. We almost have points of inflection. We do see changes in concavity. So that means because of the change in concavity here, we have an inflection point at x equals pi over 4. And we have another change in concavity, so we have an inflection point at x equals 3 pi over 4. If you needed the y coordinates for those points, you would plug those x coordinates into the original function. Now, the other thing we haven't done yet is the local maxima and minima. So we have our critical point. The critical point is pi over 2. To figure out if it's a local max or min, we would use either the first derivative test or the second derivative test. And did you know that we have already done the second derivative test? Because we have already taken pi over 2 and plugged it into the second derivative, and we got a positive. And that means that pi over 2 is a, let's figure this out, let's think about it. If the second derivative is positive, that means the graph is concave up. So that means pi over 2 is a minimum. So x equals pi over 2 is a local minimum. There we go. That completes this example. It would be pretty fun if you were to take all of this information and graph the function based on all of those things. In fact, you could grab your calculator, graph this function on the interval from 0 to pi, and then just look at it and make sure that all of these things we have figured out actually make sense. And once again, there's your homework assignment. Thank you, everybody. Have a great weekend.